So we are very happy today to have Tzu-Chieh Wei give us our IQuest seminar on measurement and quantum computation. Tzu-Chieh did his PhD here at Illinois before going off and doing a postdoc at Waterloo and then going to the University of British Columbia before landing at Stony Brook University. So next week, we actually have no seminar to the March meeting. And as usual, please use the chat function for asking questions or raise your hand. And Tzu-Chieh, I don't know if you are okay with me maybe trying to find some times to interrupt you, or if you have some natural breaks.
That's okay. I think I can stay until 3:30 your time. 4:30.
If people have questions during the seminar.
The question during seminar, please speak out, because I don't think I can see easily the raise hand or chat. It's not so easy for me.
Sounds good.
Yeah.
And a warning to everyone, we are live on YouTube. So if you unmute yourself or pull up your video, you will also be live on YouTube. So, all right, thanks, take it away.
Yeah, thanks Elizabeth for inviting me to speak here at iQuest. It's really a pleasure. I don't think I haven't been back to Illinois for a while, even though this time still not really the case, it's virtual. So today I'm going to talk to you about measurement and quantum computation. So first, I'd like to acknowledge support from NSF over the years, and including my stay at Illinois. So let me get started, see if the slide works. Okay, yeah, I think it's an exciting period of time for quantum technology. We have seen a lot of quantum devices, medium size, around 50 or more, and even 100 qubits. And for annealer, you have over thousands of qubits. So I'd like to talk a little bit more about quantum computations and introducing maybe the ultimate goal of one of the holy grail is to demonstrate quantum supremacy, as John Pascal advertised. And we also have seen the Google team has demonstrated something that they call supremacy on their 53 qubit Sigmor machine, that they have performed quite large number of random circuits. And they argue that this is not possible to be simulated by a classical computer. But however, IBM team, they argue that if you use a supercomputer with secondary storage, you might be able to do this simulations. But regardless, the experiment done by the Google team is remarkable. And whether we have a quantum advantage, we still need to wait for the testimony from whether we really have a efficient classical algorithm or not. So I think the development of classical and quantum should go hand in hand. So I'm going to just set the stage to introduce a few framework of quantum computation, as I'll be speak about them along the talk. The first is the one that you guys are probably most familiar, is the standard circuit model. You initialize qubit in certain fixed state, for example, 0, and you, according to your algorithm or function you want to apply, you apply sequence of gate appropriately composed into, for example, 1 and 2 qubit gates, and at the end you perform measurement. The second one I will be touching later is the adiabatic quantum computations. It's easy to understand pictorially like this. Imagine you have a time-dependent Hamiltonian. You want to do some computation for a certain hard problem that's encoded in this final Hamiltonian. The ground state of final Hamiltonian would be the answer, but you cannot directly access that. You start with some simple initial Hamiltonian that you can prepare the ground state. And if you have a way to time time-dependently evolve this, you will be able to let the system evolve to the final ground state, provided there's a gap. I won't talk so much about topological quantum computation, but you can imagine there's a way of using the so-called exotic particle called anion. And when you braid them, they essentially give you quantum gates. But the one that we'll be speaking toward the end of this seminar is the so-called measurement-based quantum computation, where the only thing you need to do is simply perform local measurement. It's like you have local, for example, STM tip, you look over all your atoms and perform measurement, and at the end, you get the quantum computation outcome. Of course, it relies on prior entanglement as a resource. Okay, so the focus of the talk today, or the central theme, is measurement. So I'd like to introduce a few physical systems. These may be the system you work with or you're familiar with. Well, the first one that I'm particularly familiar with is the photons, detecting photons. For example, in Paul's group, that you will see these kind of setup. You have polarizing beam splitter, filter, and at the end you perform single photon detection. The second one that I show here is taken from the plaque of commemorating the Stern-Golak experiment on silver atoms. In this case, you have a magnetic gradient, and here you have silver atom that carries spins. And through these magnetic gradient region, the atoms split into two. So this is measuring the spin. You could also have the atoms, maybe like in Bryce's lab or Brian's lab, you work with co-atoms. In order to detect whether it's up or down, and call it qubit, you apply these so-called cycling transitions, and you use the detection of the photon as a signal of detecting the bright state, for example, this one here. I think this was the first proposed by David Wine a long time ago. And I'm showing here two specific ions, for example. And maybe if you're working or more familiar with superconducting qubits, maybe, I don't know, in one of the lab, Dale's lab, that you would implementing such a measurement. And what I show here is a Cooper Bear box. See here. And the way to measure whether the state is up or down is to send in some microwave or radio wave to see the photon coming out has a phase shift or not. So these are the examples that maybe you have seen before. So as a theorist, I like to go back to the basic. You could look up any standard quantum mechanics textbook. You see these measurement postulate. What it says is there is an observable, which is a Hermitian matrix, associated with the measurement. And you imagine this observable is decomposed into its eigenbases, and these are the eigenvalues. And this is equivalent to specifying the basis that you're going to measure. The postulate says the measurement process projects the system, which, for example, initially is in the state psi, to one of the eigenstate labeled On, and you read out the eigenvalue On. And so the state after the detection is projected into one with eigenstate described by a projection operator acting on the state. And this is just normalization and related to the probability. Associated with the postulate is the so-called Bohm rule, that the probability of detecting a state in On is proportional to the overlap square. You can also write that as a projector operator and the state vector density metric and taking a trace. So I'm illustrate this with a simple example for these spin states, qubit in up-down superposition. Suppose you want to measure the observable sigma z, you orient your Stern-Galak device appropriately, and you will see the atoms go here or there with probability of up in this expression, and you will give a score of plus to this outcome. And you will get the other outcome, and you give a score -1, and the probability that it occurs is this expression. That's the standard measurement postulate. So I hope that you have seen this before. If not, that's really just defining really the basic of measurement in quantum mechanics. So yeah, here is the summary here. You have projective measurement as what I described previously. You have projection operator, and the probability is related to the trace of this expression. And these projection operators are orthogonal, and they sum to identity, meaning that the probability is conserved. Now, in quantum information, we usually deal with generalized measurement. You could compare or contrast how they are different or the same. In terms of generalized measurement, you're not going to have a projection operator. You're going to have operator F, and this combination sum over to identity. This is usually called the POVM, positive operator value decomposition. Basically, really just saying the probability is conserved. And the action of the measurement is that you map the state psi into this expression, essentially taking this F acting on psi, and PA is the probability. So they're very similar. So it's very abstract, but this generalized measurement can actually be derived from the polynomial measurement by adding a meter or enlarging your original Hilbert space. You can imagine that your system is psi and your meter state is 0, and you have some unitary evolution on the joint system. And the evolution is such that the meter is evolved to some alpha state, but the system is acted by this F operator. So that's one way to imagine how this generalized measurement is achieved. So I'd like to see if there's any question so far. Okay, so.
I don't see anyone.
Okay, if not, then I'll mention something which I will not discuss later, is the so-called weak measurement. One definition of weak measurement is to use the POVM that we have earlier. This combination F dagger F is a POVM element. One definition is to assume that each element is proportional to identity up to some small corrections. Another one is simply say, okay, the coupling of the system to meter is weak. Take an example here. You have a spin you want to measure, and you prepare your meter in certain position wave function. And for example, you couple the spin and momentum. And the action of that is that depending on the spin state, it will shift either to the right or to the left of your meter wave function. And there is some interesting notion called weak value, is that if you not only pre-select your initial state, but you also post-select the final states, you can get something and value which is actually greater than the eigenvalue of your operator SZ. So this is called weak value, this expression proposed by Arnold, Albert, and Vedman. But I will not be talking about this just for the completeness. You may wonder there are measurements beyond the projective measurement and generalized measurement. That is the weak measurement here. And I think Paul's group have demonstrated this a long time ago. Okay, so that brings me to the outline. So I'm going to speak 3 different subjects. The first one is the so-called detector tomography, and I will show you how you can take a characterized detector to mitigate imperfect readout. This work was done with my student, graduate student Yanzhu, and former undergrad student Mazia, and Dr. Xinjie Yu from Brookhaven National Lab. Then I'll move on to talk about another way of measurement can be useful in adiabatic quantum computation in a way that we are not doing adiabatic changing of the Hamiltonian, but we are doing some Zeno measurement, Zeno approach. And so this part, the work is done with my student Yanzhu, designing an algorithm for performing that kind of measurement to project to energy eigenbases. And I'll show you one particular application that you could for quantum chemistry. That is done with my student Hong Ye. The last part, I'm going to speak to you on how actually measurement alone itself can enable universal quantum computation. And we're going to talk specific about family of state called AKLT state. These are the work that I've done when I was postdoc at UBC and later at Stony Brook. But the more recent result is more on the physical side, proving the property of these Hamiltonian. So my student and I, we recently proved that the AKLT state, the two-dimensional AKLT state on certain lattices, they are indeed gap in the modern limit. So I'll summarize at the end.
Hey, Tzu-Chieh?
Yes.
There's a question in the chat before you move on, maybe, but
Okay.
I have to say it's from Felix and I don't understand it. So maybe Felix, could you unmute yourself and ask?
Sure. I was just wondering, the two definitions of weak measurement that you gave, are they equivalent via the Nymark theorem that you?
So this is more generally like abstract, and this has a sort of meter that has physical interpretation. But you could certainly, without writing explicitly this, I think this can be made equivalent by using this setup. Yeah.
Okay, thanks.
Sure. Okay, so the first part, as I said, is detector tomography. So in running quantum circuit, you need to characterize many different parts of the circuit. First, you need to characterize the state preparation. For some system, preparing the state 0, 0 is pretty easy and accurate. And then you may also need to worry about whether gates are executed correctly. And then when you read out, you have to ask the question, my device tell me that it's 0. Do I really trust the output of the device? So there are different methods for these. And for example, these are usually called state tomography, process tomography, and detector tomography. And there's actually a method which can incorporate all the three together. It's called gate state tomography. But today I'm going to focus on the detector tomography and make some assumption. For example, I will be assuming this simple state that we can prepare of high fidelity, but we don't know how accurate the measurements are. And yeah, so I will show you that just using single qubit measurement would allow you to characterize the readout. So the question that I'm asked is, suppose I send in a state, a qubit state, and my black box device tell me that it's 0, or sometimes tell me 1. I want to characterize the behavior of this black box. So that's the goal. And I'm assuming that I can send in simple state that I can prepare with high fidelity. Okay, so just to remind you the measurement, perfect measurement, projecting to 0 and 1 that I illustrated earlier, Stern-Galak experiment. You can write in these operator form, so 1/2 identity plus 1/2 of Cauchy Z matrix here. This is for getting the 0 outcome. Projector 1 is getting the minus outcome, which has a different sign in this operator. And they sum up to identity. And as I said, in general, we should treat these measurements as generalized measurement. And in particular, when we describe their probability, we need to use the POVM element and take the POVM element and your input state to describe the probability. So because it is a qubit, so we can, the only 2 outcomes, so we can write in a way very similar to these combination. We can put identity and including all the 3 Pauli matrices, and I include the overall constant. I require that these 2 POVM elements need to sum up to identity. Okay. So basically, I'm going to take this, parameterize this, the outcome, pi 0 and pi 1 using this these expression here. So when I call detector, what I mean is the detection outcome pi 0. I imagine is a abstract detector pi 0, and if it click 1, I imagine it's a pi 1 is an abstract detector. Okay, so I already said this. So we're going to send in state that we can control, and we assume that this can be prepared with error much smaller than the measurement itself. And we're going to test these on IBM quantum machines. For them, the ground state 0 is really easy to prepare with high fidelity, and the single qubit gates are of high fidelity. The error rate is of order 10 to the minus 3. So we can prepare the 6 states. We just show here the standard 0, 1, and also plus and minus 1, and the other plus minus I state or eigenstate of sigma, poly sigma 1. Okay, these can be prepared very easily. And we're going to record the measurement outcome statistics, use the collected statistic to infer what these operators are. And because, okay, let me just describe the expression here. So this is the probability of preparing a state M, and you record a click L. So that's the trace of these 2 expressions, give you the probability PLM. So FLM record the number of times that happened. So because this is a linear equation, you can infer pi L, but there are more parameters that you have. So in order to be consistent, you can use the so-called maximally likelihood function. This one actually was studied a long time ago. And the upshot is that there is a way for you to infer these operators iteratively. So I'm not going through the detail of this expression, but just to show you the result that we have. So the first example that I'm going to show you is to test on these 5-qubit machine of IBM. So I just show the outcome using these block Sophia pictures. So the first one I show you, there are the 5-qubit detectors. So this is the red is measuring the 0, and green is measuring 1. And we measured each individual detection separately, meaning that when we measure this, all the other ones are kept idle. And we measure this, all the other 4 are kept idle. We could also do these all in one go, because these are simple state preparation and measurement. And this is the result that we get. There's some slight difference, but I want to show you the important feature of the detector. So you can see that these block sphere plot show that these arrows are mostly vertical. However, the length of arrow is shorter than it could have. And you can actually see that by looking at expression. If you prepare 0 and you measure 0, this is a probability. It's a combination of these two parameters. But if you prepare 1 and measure 0, the difference of these two parameters give you that. And the difference of the two probability, conditional probability, give you the A30. A30 is essentially the length of this arrow. If it's 1, then it's a perfect detector. If less than 1, this is an imperfect detector. But we can understand this shrinking of parameter by understanding that this is basically classical error. So it could be 0, sometimes flip to 1, or 1 flip to 0. It's probably not obvious here, but you see a slight tilt. The slight tilt indicated that somehow the detector has some non-classical errors, non-classical effect, because that's in the sigma y basis and sigma x basis. But we see that these are very small. There's also the width of the arrow that I use to represent the coefficient of A0, the coefficient in from the identity operator. So for example, the one associated with outcome 0 is the probability of getting 0. When you measure 0, when you prepare 0, you get 0. That's the probability, P0/0. And adding that to that is the probability of when you prepare 1 and measuring 0, really the total probability of measuring 0. And correspondingly, there is also the one associated with detector outcome 1 is this expression, basically the probability of measuring 1. In the IBM device, 0 is the ground state. So you expect that when there is a flip, it may be flipped more likely to 0. So you expect that you detect 0 more than 1. And this is indeed the case. You see that the red arrows have wider width, wider here, and the green arrow are narrower. Okay. Yeah, I also show other results on the other IBM Q machine from Melbourne. At the time when we performed the measurement, there were only 14 qubits available. I think at the moment, this one is active, but this one is still not active. You can see that the detectors could vary. So this one is the worst. At the time we measure, it shrinks more than 40% of the error. Okay. So I show you the experiment and characterize detector. When I'm going to show you that actually they are useful for readout mitigation. So I'm going to assume for the moment that detectors are independent, they act independently.
So it looks like Paul has a question. I don't know if now would be a good time to.
Okay.
Hi, Tzu-Chieh.
Yeah, hi, Paul.
Your bad detector, or your bad qubit, let's just say that. How do you know that it's the detection on that particular thing that's bad, and maybe that the gates on that particular one aren't bad, or the initialization isn't the problem?
Yeah, we made the assumption that there's state preparation, and the simple gate are of high accuracy. But we also did not just the detector tomography, we do the full gate set tomography. That is used to characterize both the state preparation, gate operation, and measurement. That method is particularly good for gate characterization, not so good for state preparation and measurement, but the results are consistent. So this one is really the bad detector of all the 14 qubit. Yeah, that's a very good question. In a way, you could also imagine if I make the assumption that the state preparation and gate operation, simple gate operation of high fidelity, and you characterize the detector, you might want to go back and use that characterized detector to characterize your state preparation and gate operation in a way iteratively. So that may improve your accuracy. Yeah, that's a different way than the gate set tomography.
Sorry, that seems almost too good to be true, because you could imagine then you improve your accuracy on the state and on the gates, and then you iteratively go back and do the detectors, and then you use the detectors to get, it seems like you
at some point you cannot be probably the lowest, the highest accuracy in your device. Yeah.
I see. Yeah, okay, that makes sense.
There is a paper by Kneel and collaborator on that approach. So there might be other steps that I gloss over. Yeah, but you could use the full gate set tomography, but as I said, it's not so sensitive or so good on the state and detector. But they're very good at characterizing the gate. So then you know that your gate is well characterized. And if you start with 0, which is the ground state, then you have a pretty good confidence of you are preparing the right state. Yeah.
Okay, thanks.
Yeah, no problem. Okay, so you can ask, okay, now what? I know I have bad detectors. Then should I just quit my experiment? The answer is no. You can still keep your statistics. For example, these let's assume for the moment that these detectors act independently. We're going to see that they are not. But to the lowest order, let's assume they are product. These detectors act independently. And as we have characterized, it's mostly along the z direction. So we drop the xy direction. And suppose this is the probability distribution you have by performing the measurement. It's the real data. And you just write this expression, rewriting in terms of ideal detection probability distribution. This P is the ideal one. And you see that they differ by these numbers. In fact, it's a matrix. So you see that the actual measurement distribution you get is related to the ideal measurement that you would get up to this matrix. So if you can invert this matrix, then you will get the ideal measurement distribution. So I think that's at least that's the good thing about even if you have bad detectors. But this cannot be used to correct single shot measurement. Suppose you say, okay, I perform one specific measurement, I get 0. Do I really get 0 or 1? That I cannot really say. I mean, I can only give you the probability or the confidence. You cannot correct that single shot. But for most of the application, inverting the ideal measurement distribution is perhaps sufficient. So you can invert by doing naive inversion, matrix inversion, but you may get the P, the ideal P, to have negative component. Then you need to truncate. It's very similar to state tomography. So I just give you one application. So on the 5-qubit device, we prepare this fail state. Yeah, the ordering on the case is the reverse. This 0 is here, and the most significant digit are the circuit here, down there. So we prepare this simple fail state by using Hadamard and CNOT and perform the 0-1 basis detection. And this is the raw data we get. We have mostly 5-0 and 2-1 here. But we also have non-negligible component. So for example, this 1 here was the last stage. This one, you could have some probability ended up at 1, even though we're not doing anything at that. So if we perform that inversion using the characterized detector, we find that these other components become smaller, much smaller than the 2 dominant one. So this is a way to use the characterized detector to do something useful. At least maybe the CNOT gate were not as bad as they thought initially. So in order to characterize the error of CNOT, I think that you need to also take into account the detectors are not perfect. Yeah, but I would say that this is very specific to this system, that the measurement error are high, but for a system like in photon polarization, the detection is pretty accurate. So that maybe you have to look somewhere to characterize maybe the state or the gate. So the assumption that I made for the mitigation, I assume there's no tilt, but actually we can lift this assumption provided we have access to perform additional gate. This is the original circuit. If we can add these Z gate at the end randomly and collect the statistic, we can still assume that there's no XYZ because Z basically cancel out anti-commute with the XY component, and when you add these statistics, it basically cancel out. So you can assume that you can still use the previous procedure. Okay. You could generate to multiple qubits. So you write detectors in terms of these 2 to the n combinations, expanding those in terms of polymatrices. The state you send in are still simple state. You send in product of these 6 states. If you want, you can reduce down to 3 states. We have done this to up to 3 qubit detector tomography. And we have also done mitigations. But the number of measurements that need to scale is exponential large. So there's still an issue of how do we deal with these for large systems. I want to mention that IBM have similar implementation in their KISS-kit. So they basically prepare standard state and measure the probability of getting that. And you invert that. This is exactly that we had earlier. So maybe one more application of the detector tomography is we can use this to infer, is there a detection crosstalk? So what we do is we take different way of characterizing a detector. For example, if I do a 2-qubit detector tomography, and this I do one single one, then I trace out one of the qubit here. And the ruler represented, we just measure the distance of these 2 outcomes, and we come up with a table here. The one that gets traced out is the end of the arrow. If this is big, then we have a thick arrows. So for example, 2 affect 3 quite a lot here. We could also try different way of characterizing the detector. This indicating we capture all the detector in one go. And this is the so-called mutual influence diagram we obtained. If you don't perform these, so here we don't perform these simultaneously, but if we perform these 2-qubit separate detector tomography, but simultaneously done in one circuit, this is joint 2-qubit detector tomography. You see that there is the influence is down to this. So what I would conclude is that when you have all qubits operating together and compared to you have one or detection operating as, alone, they are different. And even when you're operating almost in the same scenario, they still have crosstalk. But we have not resolved the physical reason. I mean, they are coupled physically, but we have not identified why these talks, where they come from. At that time, we don't have access to other way of characterizing the measurement. Okay, so I just show some of the related work. In particular, these 2 papers, they deal with measurement that have pairwise errors, but I don't have time to go into that. So I'd like to pause to see any question at this point. Okay, if not, I think I'm running behind of what I planned, but it's okay if I don't finish the talk. Okay. Yeah, you can ask me. Okay. So the next, going along these, I'm going to look at the adiabatic quantum computation, but from the measurement viewpoint. So so these adiabatic quantum computation, I think, was advertised by Fahy and collaborator. Was actually looked at earlier by Nishimori and Kadawaki. The idea is really just dragging the ground state to the final ground state, provided there's a gap. So, and it's known to be universal. It's equivalent to the circuit model that I described earlier. But there's another way you could implement this, is to use the so-called Zeno effect. If you can perform measurement, let's say you discretize the time and you measure at the energy eigenbasis at this time study events of the point here, then you could, with high probability, drag the ground state, project the ground state to the next ground state. So this was explored earlier in this paper where they discussed in the case of classical annealing. So yeah, schematically, this looks like this. You perform measurement, eigenbasis, and so this allows you to probabilistically advance the ground state. Yeah, if the dots are dense enough, the effect will be identical to the adiabatic quantum computation. So you might ask, which one is better? It depends what control you have. If I can adiabatic control and change the time-dependent Hamiltonian, this is probably is very good for you to do that. If not, and if you could perform the measurement in the eigenbasis, then you will be able to do that. But performing measurement in the eigenbasis maybe not easy. So that's the topic of my slides here. And this, from the quantum information point of view, this can be achieved by the so-called quantum phase estimation. And assuming that you expand in eigenbasis, you do the so-called phase estimation procedure, and you read out the phase that at the same time also project the state to the eigenstate. But let me show you the circuit. The detail is not so important, but the idea is that you prepare some ancillar qubit in the plus state, and you do these control unitary, assuming this U operator. Yeah, I'm missing a state here. Let's see if I can add that. Control. I'm missing a U here. Okay, so assuming that this could be, for example, evolution operator, and this U is eigenstate, you have a phase or energy you want to estimate, and you use additional ancillary qubit to record the phase. And the design of circuit is that you have an exponential shift, or U to the exponential power, that sort of shift the phase of this. And at the end, you perform the inverse of quantum Fourier transform, can read out the phase. It looks quite complicated, but it relies on the control evolution. So if the ancillar state is 0, you do nothing to the system. If it's 1, you do a conditional evolution. But the evolution time has to be 2 to the k. K runs from 0 to t minus 1. Okay. So what I'm going to describe next is a simplified version that would achieve the same phase estimation. So in some sense, I take one element here and look at one instance of that, and I don't have inverse quantum Fourier transform. But in this case, I'm assuming that I can do these control evolution. This H is my Hamiltonian, or the observable that I want to measure, I want to project to its eigenstate. So I would have a 1 qubit ancillar. This ancillar can be in arbitrary pure state. It doesn't need to be in the plus state. And I also can vary t arbitrarily. I don't need it to be 2 to the k. in fact, you could also fix the delta t. Compared to the previous case, you would have to run the t from 2 to the 0 to 2 to the t minus 1. Okay, so I'm going to argue or show to you that by iterating this procedure, meaning that I do these coupled evolution, I perform the measurement on this ancilla, I throw away this ancilla, I take another ancilla, perform the same coupling and measurement, and keep iterating this. And I know that it would, I'm going to argue eventually it would project the system into an eigenstate. Okay, and I also want to mention that this can also be characterized. If this may be important in when you want to approximate the gate. Okay, so I'm going through this analysis, assuming this ancilla is this arbitrary pure state. This is my system. I apply these control unitary in a sense that there are two branches. One, there's no evolution. The other is the system evolved by you. And I'm going to measure the ancilla in a superposition basis with 0 plus minus 1. Essentially, this phase, it can be you can get rid of this phase. But for the analysis, let me show how it goes. So suppose I measure in this basis, then the system would collapse to a sum of the two branches. So one from this branch, the other from this branch with the phase and the beta. But you see the phase and beta, they come together. So this phase can be absorbed into the preparation of the ancilla. So I'm going to just set the psi here to be 0. This meaning that you measure in the poly X basis. So, and the probability that it occurs is the norm square of this normalized wave function. Okay, so this is the unit that I'm going to base on. Okay, so I'm going to look at two physical properties. The first is the energy. So it's pretty simple calculation because you have two different outcomes. You just measure the energy, measure depending on the outcome, you measure the expectation of h with respect to the psi prime, whether m is 0 or 1. I want to look at how the energy has changed. So I subtract the initial energy of that. And I see the expression here, if I assume arbitrary alpha and beta, and going to take delta t to be small. In the case where the combination alpha star and beta have non-zero imaginary part, this energy change is proportional to the energy variance. Okay. And when you use this specific combination of the ancilla state, you have these h cube and h square and h combination. Yeah. So, but from this expression, it indicates that we should actually look at the variance itself as well. So I'm going to do the calculation, but this time I'm going to measure the average energy variance. So if I have output, so outcome 0, I measure its variance and weighted this probability, and I subtract the original variance, energy variance. So interestingly, I get similar expression, very similar. This variance square and square. And I have these coefficient because the constraint alpha and beta are smaller than 1, they square to identity. You can easily see that this expression is with a minus sign here is less than 0. So what this means is the average energy variance decrease on average. So when it decreased to 0, that means that it reached to an energy eigenstate, right? An energy eigenstate has no energy variance. You could also analyze if you use these specific plus and minus state. It's actually related to the h cube and the corresponding expression here. Okay. So I'm going to show you by simulation to demonstrate to you that the variance, in fact, not the average, the variance itself actually dropped to 0. So I'm going to take this 5 by 5 random Hermitian matrix shown here. This is random Hermitian. Assuming I have a control operation that I can do here, and I'm going to fix an initial state. It's randomly chosen, and I'm going to take combinational and input ancillary to be of this particular form. Phi could be a random phase, but I take these way to be the same, 1 over square root 2. And I'm going to do the numerical simulation and stop when the energy variance is less than 10 to the minus 10. So just to remind you that these are the 5 different energy. And I show different way of doing the iteration. For example, if I allow my t to vary from one instant to another, I see that it converges very fast. And when phi can also be chosen to be random. But I want to just point out, you can fix your t and allow the phase to vary. You can also allow you to get the energy to be fixed at the end. And these are corresponding to 4 of the energy. But the strongest evidence is that you see these energy variance, they drop to 10 to the minus 10. And different way, control different way of convergence. So want to pause here to see if you have any questions. So this is numerical simulation showing that the energy does converge. But I think the strongest analytic support that I can give is to show that the average energy variance does decrease monotonically on average. Okay. So this means that if I use this setup and iteratively, I can actually project the system into eigenstate of H. So even though I have not done anything, I have not done measurement to the system, but only coupled to the ancillary, and then it would drive to the energy eigenstate. This, you may interpret that this is kind of weak measurement, that after so many iterations, it drives the system to eigenstates. So this is one illustration of application that we can simulate. We take this Hamiltonian. Imagine I have the diagram of the adiabatic, but choosing discrete time. And I measure in the eigenbasis, projected energy eigenbasis, and I record the energy along the way. So different curve represent different number of qubits of these transverse field Ising model. And I also record the variance. This is numerical simulation, so I can calculate those. And you see that the energy variance is most dramatic in the middle. In the middle is really the transition point. There's a quantum phase transition in the thermal limit happening at g equal to 1/2. Okay. Yeah, so we have not been able to do this on actual machine because running this would require a lot of iteration and the system may not be coherent at this point. Want to show one possible application in quantum chemistry. You can measure the energy, the ground state energy of a H2 molecule, depending on its distance and angle. And you can start from some simple Hamiltonian and connect that to the molecular Hamiltonian. And if you look at the spectrum, you see that there is a huge gap. So that means if you can do an adiabatic, it's also very good because there's the finite gap. But for measurement, you could as well reach to the ground state. this is for the part at equilibrium. We find that for larger molecular distances, the adiabatic does not perform very well because there are energy level crossing. So really the Zeno approach become a good a method there when you have degeneracy. And this also allow you to access the excited states. Okay, so let me pause here. I think I only have a few more minutes, so probably won't be able to go through the third part.
Yeah, and Paul's got a question too. So.
Yeah.
So the obviously in the adiabatic approach, you have to go slowly enough that you don't jump the gap. And the question is whether or not there are limits in this Zeno-based scheme in terms of how rapidly you're making your measurements. Does this allow you to somehow get more quickly from point A to point B without taking yourself out of the subsystem?
I would say it's similar to the typical adiabatic approach, because you need to worry about the overlap of your present ground state to the previous ground state. If you have a gap, then they are connected. For example, if you just have a simple level crossing, they are not even related. So you just go straight crossing that level.
I see.
Yeah,
and do you have to worry at all about the anti-Zeno effect, which is that if you, depending on what your reservoirs look like, you can actually self out of the initial state more quickly rather than
so
locking yourself
that's a good question.
State?
So here I'm assuming I'm doing the perfect projection. So in real life, I probably have to worry about whether I would have anti-Zeno effect. Yeah, but this is not taken into account. Yeah.
Okay, thank you.
Yeah, sure. So I don't know what I should do. Maybe I would just say the fourth approach of measurement base is built on a highly entangled state in the beginning. Let me just walk you through quickly, but I want to give you the key point of that is that you start with highly entangled states, and the only thing you need to do, let me just go to the next, is you perform single qubit measurement. In this case, suppose you want to simulate this circuit. What you do is you use a poly Z measurement on this particular so-called cluster state. I won't have time to explain what that is. But if you have done that measurement, essentially it removes these qubits out of the picture and the remaining entanglement structure is still the same. Then you perform measurement along these wires to simulate one qubit gate. And the measurement that get performed near the bridge here allow you to simulate a control NOT gate. Yeah, so I think I'll just skip this. How do I click? How do I back to the pointer? Is it? How do I click? Yeah, the question, how do I click unit? Yeah.
If you escape, you can go back to a normal pointer.
Okay. I discard. I have some intermediate slides that will explain that, but I don't imagine that I'll be able to do that. But just to show that this cluster state, or more generally measurement-based quantum computation, somehow revise the linear optics universal quantum computation, because in order to implement the original KLM scheme, it has required high overhead in performing the entangling gate. But if you could build up the resource right up front, in some sense, it's pushing the difficulty under the rug or to the beginning, but it's really independent of what gate or algorithm you want to run. If you can prepare these entangled states, then you'll be able to perform quantum computation. So what I wanted to talk about, I did not have time, is talk about specific family of state called AKLT states, but I will probably skip this. And associated with that, there is the so-called Hamiltonian. And the question that I plan to talk about was, this Hamiltonian is expected to have a gap, but so far hasn't been proved until recently. We and other group independently do that, but I don't have time to do that, the detail. But if you're interested, ask me independently, but sorry, I have to run through this. The point is that we can prove the gap almost rigorously for these various number of lattices. So maybe let me just jump to the conclusion. Here. Okay, so yeah, so I introduced detector tomography, and we implementing this on IBM-Q, and also propose way to mitigate the measurement error. And I discussed to you how we could use a simple scheme to project a system to energy eigenbasis, and that could be used to replace the adiabatic quantum computation. I did not have time to talk about these measurement base in detail, but there's possible directions that one could think about is to make the detector tomography efficient when you have large number of qubits, and make the projection algorithm maybe suitable for next machines. One thing that I did not have time to talk about is the non-zero gap of these AKLT model on the square and calculated lattice are still open. And maybe one could also, I was going to tell you about the quantum computation for the AKLT using the AKLT state, but this is the state and this little dot here. We actually generate we actually look at the phase diagram by deforming that, and if one could show that entire AKLT Hamiltonian phase is universal for quantum computing, would be cool. So let me end my talk here, and thank you very much for your attention.
Thank you very much for a great talk.
Thanks.
You're getting some hand claps in the Zoom.
Yeah.
So are there any more questions for Tzu-Chieh now?
Yeah, so I'm going from more practical to the less practical according to my talk design.
So we do have one question in the chat. So the question, a quantum computer can typically perform a binary measurement on each qubit. How can these devices implement an arbitrary POVM on a d-dimensional Hilbert space? For example, a 7-outcome measurement of a qubit state.
Yeah, so that requires you to have more qubits. Yeah, so if you pack enough qubit, then you can essentially use other qubit as sort of a meter. Let me go back to that's a good question. Let me try to find the appropriate slide.
And Brian, feel free to unmute yourself if you want to reword the question though.
So it's this slide. So if you have more than one outcome, more than two outcomes, you need to have additional meter that can record that outcome. One naive way to think of that is, yeah, adding one more qubit or two, or yeah, essentially, however many outcomes you need to have in enough level to record that state. Yeah. I hope that answered the question.
I think so.
Thanks.
Yeah. Yep. Anybody else? All right. Well, then, in the interest of time, let's just say thank you again for a great seminar and for agreeing to come give a virtual seminar here.
Yeah, thanks.
And we will see everyone in 2 weeks.
Okay.
Thanks, Tzu-Chieh. See you in a little bit.
Yeah. Should I go to the
Yep.
other